Okay, so for anyone who doesn't know me, my name is Peter Horn. I've been working on standardization of their architectures using LabVIEW and TestStand, building large systems, basically trying to make sure that they write the best software possible. So she asked me to come and talk about this new couple of data types in LabVIEW, sets and maps. Something that's pretty new to a lot of people, so hopefully it'll be interesting and give you some ideas about how you might want to use them. Before we get started though, I wanted to give a shout out in the Our Giants Are Female as well. So the lady that I chose is Margaret Hamilton. She was very high up in the sort of list of people writing code for the 1969 Apollo 11 mission to the moon. She added things like there's a system to add priority alarms in there, so it would interrupt the astronauts' display if there was an emergency going on. The PC was not PC, but the computer was overloaded, giving them a kind of a no-go landing decision. She was also fairly responsible for developing some early weather prediction software, publications on chaos theory, and she just generally did some pretty cool stuff alongside a few other sort of interesting engineers around at the time. Quite a lot of them were female as well. I particularly like this picture of her standing next to the code written for the Apollo 11 mission, and it's taller than she is, which is pretty amazing. Also wanted to thank a couple of people before I kind of dive into LabVIEW sets and maps. So this guy, Primary Piotr, I don't know how to pronounce his surname, but Piotr, he works in our engineering, solutions engineering group over in Budapest, and he's very passionate about LabVIEW architectures, new things in LabVIEW and doing cool stuff. He had this Twitter handle called LabVIEW Sets and Maps, where he did a series of posts about some of the cool things that you can do with it. I've taken tons of my ideas and some of the screenshots of LabVIEW directly from his Twitter video. It made my life a lot easier having that available. Unfortunately, he didn't have a set of slides that I could just rip off straight away, but never mind. I said I'd share these ones back with him. Another person that's been doing a lot is Christian Altenbach. Anyone who came to NI Week or was watching NI Week online may have seen this presentation they did where he was talking about LabVIEW sets and maps in that. It is available on YouTube. Unfortunately, I don't know what happened with the video recording, but you can see the slides kind of crooked. It's just an awful video recording. But the stuff that he was talking about is actually genius, but the recording is awful. I don't know why. You can watch the video on YouTube, or you can go to LabVIEW Wiki and you can download his slides from there as well if you want to take a look. So there's a lot of good stuff there. But again, I've taken some of what I've talked here directly from Christian's slides as well. So what are we going to talk about? First of all, what are LabVIEW sets and maps? What are they good for? And kind of what are they really optimized for, and why are they brilliant? I've got a bunch of example use cases. They're all pretty simple use cases, but hopefully they should kind of spark some ideas off for you and give you some thoughts on how you could expand that and sort of integrate it into your own applications that you're building. There's some other kind of slightly cool stuff to do with them. Just a couple of things that I thought were worth mentioning that may not be kind of immediately obvious that you can do with them, but just make them a little bit easier to use. So I thought I'd put that in there. And then I also did some sort of performance comparison, comparing maps to variant attributes and sets to arrays. As they do quite similar things, but there's some differences both in terms of what they can do, but also in terms of performance. So if anyone's got any questions at any time, feel free to shout out, by the way. So to start off with, what are LabVIEW sets and maps? If you go into the LabVIEW help, you'll see the stuff over on the left here. Sets are basically a collection of, it's very small that text actually, isn't it? So sets are a collection of unique elements of the same data type. Basically, it looks very similar to an array. A couple of different properties though. First of all, it's sorted into order. So if it's numerics, then numeric order, or alphabetical order for strings. And they're all unique in there. It's can't have a duplicate element in there. So if you try and add a second, if you try and add one to it and then another one, then they'll only have the first one in there. It won't have added a second one in there. That means it's very optimized for sorting through and looking through to see what's in there, because LabVIEW doesn't have to search through the entire thing to find something. It just knows where it is very quickly and easily. And then maps are a collection of entries consisting of key value pairs. The keys have to be unique. The key and the value can both be any data type you like. So it doesn't have to be a string data type like with variant attributes. You can have a cluster, a class, whatever you like. And that makes it really quite flexible. And then for both of them, we have a bunch of functions. So we can do things like insert new data into them, we can look in them, remove information, convert them to arrays. There's a bunch of additional malleable VIs here that are useful for doing some sort of preset functions. It's worth noting that some of these malleable VIs also work on the maps section, even though they're in the set palette. Some of them work on maps. And that's because it's quite common to have a map of sets or a set of maps that you might want to work with. I can't remember exactly which ones. I think these outside 4 should work with maps. It's probably the set Cartesian product that doesn't. So what are they good for? I kind of mentioned some of this already. Effectively, or essentially, having information, you can have petabytes of information that you've built up over time. That's kind of useless. Thanks. Yeah. Having information is pretty much useless unless we can find it efficiently. So sets and maps, they're very optimized for storing information and then efficiently searching for it. And then also they're very well optimized for dynamically changing that data. So adding data into it, removing it, replacing a value. In some cases, you can do this much more efficiently than you can with something like an array or variant attributes. And then you can basically build diagrams like this. Just a quick mention on what these four VIMs do. So first of all, we've got set union, which basically first set plus the second set, but obviously with any duplicate elements removed and then sorted into order. First set minus the first set is set difference, again with any duplicates removed and so on. Symmetric difference is elements only appearing in one set, and then intersection is elements appearing in both sets. So if you want to do something like that, then building it into a set is very quick, and these functions operate very quickly. I think pretty much everything else in the sets kind of palette is pretty self-explanatory. Is there anything up there that's not clear what it does at all? I think things like, you can imagine read, set, max, and min, that's going to be extremely quick to operate. So all it has to do is take the first element and the last element. It doesn't need to search through the whole thing like it would with an array, max, and min.
Sorry, Peter. Convert set to array. Do you have convert array to a set? Is that possible?
There's not a pre-built function, but it's very easy to do. You just put insert into set into a for loop, and you'll see that in some of the examples in a second. So, some of the things that you can do with sets. Has anyone ever built a piece of code like this, where you've got 2 data sets that are arrays, and you want to have all of the combinations of both arrays? So the first element from this with the first element of the second one, then second element of this with the first element, and so on. So you get 4 pieces of data in total, and you want to iterate through them all. Anyone ever created a piece of code that does something similar to that? So if you create them into a set, then you can use this, what's it called, set Cartesian product, or the one in the middle, I can't remember what it's called. Set Cartesian product. And that will compute all possible combinations of the 2 sets, and then output it as another set. And then, because of the way that sets work, you can just put that into a for loop with auto-indexing, and it will just iterate through all of the elements in the set. Another pretty cool thing if you want to find what all the unique elements are in the array, in an array, as I said, if you put it into a set, it automatically gets rid of any duplicate elements. So if you just put that through a for loop and do insert into set, and then this boolean out here will tell you if that was a duplicate element, and therefore you can just find out how many duplicate elements there are, and get your either get it out as an array or as a set. Has anyone seen this remove duplicates from on the array function? That just uses a set inside, and it does exactly that. So because that uses a set inside, when I was doing my benchmark and I wanted to remove duplicate elements from my array, I sort of thought I can't really use that, so I had to manually do it, which is made things slower, made the difference bigger between sets and arrays as well. Okay, does that everything make sense so far? That's kind of all there is to sets, really. They're pretty simple. The things you need to remember are just that they're unique elements and they're sorted inside into order, and then you can pretty much do anything you like with them. Maps, a little bit more complex. So maps are a collection of unique keys with values. Both the keys and the values can be any data type you like. The default data type is a string, and obviously some of the examples that this is one of the shipped examples. The data types are string here, so all this loop is doing is looking for spaces in that count of words in this text string. So it gets individual words out, and then it just passes those into the set, tries to add them. If that value exists, then it adds one to that value in the one to the number representing that word, and then basically counts up how many of each word there is in there, and then it removes any ignored words, and then gives you some text out here. So it's a pretty simple example, but that kind of shows you the type of thing you can do and how easy it is to build up a map. This in-place element structure here is very useful. There's 3 different modes that you can operate this in, so you can add or modify an entry. What the other one? I've overreached myself there. I shouldn't have mentioned that because I can't remember what the other ones are. One of them is do not add entry only. Do not add entry, or do not add if it doesn't exist, I think is one. But yeah, I'll show you later maybe. Again, we've got a set of functions here. So again, we can do things like convert map to array. We've got that in-place map axis, which is pretty useful. And then pretty similar functions. So we can build a map, we can insert into a map, then we can do things like look in map and get the size and so on as well. So they're not too different. That registration map subpalette is pretty useful. I've got an example that shows what that can do in a second. But a couple of ideas on how you might want to use maps. So we've got this translation utility. It's one idea that I saw on Piotr's feed. So if you build up a series of maps with different languages, so you can say here we're in Polish. We build a map of all the different words and what does cat mean, what does dog, well, what's cat in Polish, what's dog in Polish, pies apparently, what's parrot in Polish, and so on. And then you can obviously extend this second map down and have French, German, other languages. And then we'll look in map here, so on the Polish map, and then we want to find what's dog, and we get our answer out. That's not just restricted to actual sort of spoken language translation. You could do that for any kind of translation. I can't think of any ideas, but I'm sure there's lots of other things you could use that for as well. So, just noticed I should. You can't read it, can you? It looks great on my screen. Essentially, what I'm trying to show here is we've got a central service module. This could be, say, you're using DPMH or PAX framework or something like that. Is there a question online? Oh, okay. Imagine you've got some central module or user interface or something controlling your application, and that's starting off other modules that could be actives, DQMH, or some way of launching a separate process. And within the central service module, you want to maintain knowledge of which other modules you've started and what sort of capabilities they have, or what's been assigned to each of those modules. That set of registration maps that VIs that I mentioned was in a subpalette.
There's a question, sorry, I think it's a little bit back. Do the map need to have all the value elements of the same data type?
Oh, I'll go back. So you mean this data type here in count? Yeah, that's set per map, so that has to be constant. You could obviously set that to a variant or something and then have sort of a flexible data type there if you wanted to. But yeah, essentially that has to be the same for all the elements.
Thanks, Massimiliano, for the question.
Okay. So with this registration, guys, essentially what we're doing is, this is one of the shipped examples. You can have a look at it and play around with these cells. But every time I'm clicking on register for one of these guests to register a hotel, it's launching this process, which is hotel cleaning service. And then it's storing inside its map, which is inside the main VI here, the information about which guests have been registered for which hotels. So then when I go into check registration, it asks, gets that particular map out and says, which guests have you got? And sort of formats the string. So you can see here, do cleaning services, what's actually starting those VIs. It's just a bit of VI server that opens or shuts one of those VIs. The VIs and the cleaning service VIs themselves don't actually do anything. They don't have any intelligence. It's just a kind of a VI to have something on the front panel. Obviously, in the application, and then in the registered hotel and unregistered hotel, that's where I'm using these registration and unregistered VINs, which are pre-built malleable VIs that ship with the Maps API to allow you to do this kind of activity. And then all of the other VIs that I think I showed in the video are just formatting strings. Doesn't actually look, this video doesn't look very good, does it? Does that make sense what I've just said there, or do you want me to just get the example up and I can show you? Does it make sense? So another thing that you can do is decision trees. So has anyone ever built a piece of code like this at the top where you've got several different data types and you have basically nested case structures to say, if it has this one on input 1, then look in on input 2 and then go down and down and down. Instead of having nested case structures and probably having very similar code in lots of different case structures, what you can do is make the cluster of data your key. And then basically say, if the cluster of data matches these values, then I'm going to get this VI reference and run that VI. So when condition values 10 matches what I've got in those 4 inputs there, I use VI server to run this VI, and then you can do something a bit more. Well, you don't have to have this nested case structure. You kind of build out into sub VIs instead of one big flat VI. So that can work quite well.
So that basically means that you might end up with a very large number of VIs.
Yes, potentially. So yeah, again, as with anything, there is another option, and some will probably be good for some use cases, less good for other use cases. You can do basically the same thing with error handling as well. So you could say, if I get error 5004, then world's ended, run this VI. If I get 5003, run this VI, and so on. Another pretty clever thing that found on Biotra's feed was if you've got a function here that takes a really long time to execute, then instead of every time it gets called, basically remember the values of it. So we've got to put the map into a functional global variable, a feedback node, and then values come in, and you say if this gets called again with these exact parameters, I already know the result of what's going to come out of here, so don't bother running it again. Just get the values out of the map, and then go on your way, and hopefully you'll save without execution time. Again, I wouldn't use it on every VI, but it's potentially useful. So there's a little option there. Okay, so just a couple of other interesting things that you can do. So I showed this in some of the earlier examples. You can index a for loop if you want to, both on maps and sets. So if you have a set and auto-index into a for loop, you just get all of the elements out one after the other, just as if it was a 1D array, and that's potentially very handy. Yeah, I was just going to say, if you put the convert to array function down on libraries, you actually just get a for loop there, and it just has an arrow pointing saying pass your map or pass your set in here. So that's how that works. You can do the same with a map, and you get a cluster with all of your key value pairs. It's a good idea if you're going to do that to name them in the constant over on the map, so that the cluster has named values there. And that just helps with documentation of your code. Another pretty interesting one, I only realised this morning actually, when looking through Christian's slides, is that if you have a set and you've got a load of data in your set, pass that into a file, then you can just pass that in straight into a binary file write function, or read straight out to a binary read function. And you can see by the size of the file on disk, I've got 1,000 doubles in there. It's exactly 8 kilobytes. There's no overhead for the fact that it's a set that you pass in or anything. Okay, so actually, before I go on to performance, that's kind of what you can do with sets and maps and so on. As I said, they're just a few very simple ideas. I'm sure you guys will be able to kind of expand on that and implement a lot of crazy algorithms and things in your applications. Does anything there not make sense, or anyone got any questions about anything I've been through so far?
It's probably very simple. When you pass something, a value into a set, then the set automatically puts it in the right place.
Yeah. Okay, so moving on to performance. If you just Google LabVIEW sets and maps, there's a few things that we come up with, and one of them is this discussion forum on ni.com about performance of maps versus arrays. And Christian Altenbach came in with some performance benchmarking he'd done, and it kind of had all this. I initially put this in the slide and said, here's some benchmarking. And I kind of thought, I can't really explain it very well, so I decided to do some benchmarking of my own. So this is where I'm going to get people to sort of say what you think is going to be faster. So first of all, this is maps versus variant attributes. So on the left-hand side here, I'm building basically a map. I've got a variant attribute. I'm sticking some number of random double floating point numbers in there, depending on what I'm setting this count value over here. And then I'm going around and I'm searching for 10 values from that. Now I'm doing exactly the same thing here. I'm putting the same values in, and then I'm using the looking map and then the in-place element structure, and then convert to an array to get those values out. So first of all, in terms of building the table, anyone think variant attributes is going to be faster or maps faster? Maps? It's kind of a safe bet, isn't it?
Just the word reason you're presenting.
Yeah, that's fair. How about getting the data out? We've got using variant attributes, looking map, in-place element structure, or convert array. Convert array. Anyone want to have a go at guessing which one's going to be fastest or slowest? Maps fastest, yeah. Which one? Yeah. Wow. Okay. So to do this, I wrap that bit of code in a big sequence structure with some benchmarking stuff.
So proper CLA architecture.
Oh yeah. It's high quality code here. We're talking.
Use the Zoom function.
It's not in XG.
You don't have a note saying don't do this at work.
The note's implied. Okay. One thing, I had to randomize the order of the tests. I realized that with the convert to an array, it was actually taking longer to do, and I did them 10, 100, like did them in strictly in order. Convert to an array was taking longer to do, put 10 elements into the array than it was to put 10 million in. So, well, that's not right. So I randomized the order of the tests, and that seemed to sort that out.
First set of benchmark would be skewed because the for loop is outside, and that could run parallel to the sequence structure on the top. So, I'm sorry.
Tough crowd.
I think
So-
we need to benchmark the benchmark.
Yeah,
Especially if Altenbach is listening to this, he will come back to you, I'm sure.
he probably will.
It's one of his pet peeves.
Yeah, Stephen Mercer as well. Whenever a customer emails him and says, I've benchmarked this piece of LabVIEW code, he's like, no, you haven't. Unfortunately, I've not shown this to Stephen or to Christian.
That's all
I
right.
don't
We
think
can
I've
have on YouTube. That's why we're recording it.
Yeah, never mind. So, first of all, this graph on the left is building data. I ran each of them, the tests 10 times. So there's 10 times, the variant attributes 10 times, the maps 10 times for each of these number of entries into the table, or into the array. So started off with, well, it didn't start off, but smallest was 10, then 100, then 1,000, 10,000, 100,000, 1 million, 10 million. And then on the left-hand side, we've got the time to build the table. So that's going up from 0 to 25 seconds. And obviously, lower is better. So the blue entries are the variant attributes, and then the red are the maps. And you can kind of see, well, to my mind, these ones here, kind of in the middle, they're kind of outliers. Certainly the up till 10,000. There's only one sort of one of the times round, one of the 10 times round for these three has kind of gone a bit higher. The other 9 for each of them all clustered down the bottom. Starts to go up a little bit more for 100,000, a little bit more again for 1 million. But kind of to my mind, they're pretty much equal until you get to maybe 10,000, and then maybe there's kind of a bit of a difference at 100k. But I think the clear thing to me is that as the data set gets bigger, maps become more and more efficient. Whereas down at sort of 100 values or so, there's not that much difference. I'm going to zoom in a minute on both charts to see a bit more detail. But before I do that, on the right-hand side, this is all of the searching for values in those arrays. Or we've got variant attributes, looking maps, in-place element, convert to array. The top 3 there are all clustered right down here at the bottom, and the scale's been offset because convert to array is so inefficient and not good for that particular exercise. So if I zoom right in, then again you can see that maybe at 1 million here, then in terms of building the table, then most of the maps are a bit lower. There's a few up there. I'd say they're pretty even until you start getting bigger than 1 million. There is one interesting thing that happens over here on the right in terms of searching for data, though. First of all, convert to array is way off. Takes a longer time, even from 100 elements. variant attributes and looking maps are kind of pretty constant, pretty close. The in-place element structure is kind of the star of the show, though. It's kind of right down there at the bottom, taking very little time to search through, even a 10 million element map. So I thought that was pretty interesting. Any questions about that? All sound okay? So, doing the same thing but for sets. I've not gone into all the detail about the code that I built, and I'm pleased now that I didn't, because you'll just rip it straight. So again, with this one though, I built 2 data sets just because the functions here from these things you can't really see very well are those 4 pre-built malleable VIs for difference, union, symmetric difference, and intersection. So I basically tried to do exactly the same thing using loops with an array. And so I built 2 data sets there for the array, and then 2 sets here over on this side. So you can probably guess which is faster. Sets, I'll give that one away. Anyone? I wasn't going to click there. Anyone want to guess how much faster sets are than arrays? Maybe as an order of magnitude, sort of 10 times, 20, 30, more. 20 times. So it's kind of interesting. For building, again, we've got the same thing. So building the data sets here, there's a few outliers again, but I think they're fairly similar. I only went up to 100,000 elements this time rather than 10 million, because in terms of searching through the data, the arrays were so inefficient. You could see 420 seconds for some of the operations. I was sat there for about even with 100K, it took nearly 3 hours to execute the other day. So 10 million, it was just going to be there for days. If I zoom in though, you can see they're not too bad for sort of up to about 1,000 elements. 10,000 elements, there's definitely kind of a noticeable difference in that all of these blue ones here have different colors of different operations for arrays, and they're definitely noticeably higher than the kind of the red colors for the sets. But at 100,000 elements, ranges from 0.05 to 0.3 seconds for sets, and it was, go back up, sort of 40 seconds to 420 seconds for arrays. So I did a rough calculation. It was between 133 and 8,200 times faster for sets. For those particular operations, there's obviously tons of things that you can do with arrays that we don't have the functions pre-built for sets. So I'm not saying don't use arrays anymore. There's definitely times when you need an array, besides if you need duplicate or non-sorted arrays. Does that all make sense? Any questions there? Okay, so that's kind of the end of my slides pretty much. In summary, the sets and maps are another tool in LabVIEW. They definitely don't replace anything or make anything that's currently in LabVIEW obsolete. They do give you some new options, and especially if you need to do things like building a flexible data table that you can quickly and efficiently search through, then they're really good. I know some of the tools that sort of people in NI and customers have written using sort of variant attribute tables to store sort of complex data probably would be worth rewriting using maps at some point if they're sort of in regular use. They enable a lot of new ways of building algorithms, things like that, the decision tree and a few other bits and pieces, kind of the cohesive, I can't remember the name of the function now. Mine's gone blank. Where you join 2 sets together, basically, and get all of the iterations. Those are things that should be sort of much quicker and more efficient and easier to program using maps and sets as well now. So in some areas, they should reduce some complexity. In some areas, they should be high performance, especially if you have very large data sets. but they don't eliminate arrays or variant attributes at all. Bottom line, potentially very powerful tool to understand, but again, like all things, you need to kind of understand, and if you know all the tools and things that are available, then you can make the right decision on which to use at any one point. So with that, this QR code will take you to the GitHub site if you want to download any of the demos, and if you do want to have a look at my apparently terrible benchmarking code, then feel free. It's on the GitHub site, and you can download it and take a look through it and rerun the benchmarks if you like, or any of the other examples that I put together. Some of the examples that I showed, though, were just the shipping examples that ship with LabVIEW 2019. So you'll have, if you install 2019, you'll have those already installed. Is there any questions at all before I finish?
What do you think? So obviously, for me, this replaces a lot of the use case of variant attributes of doing lookup tables because it's an efficient way to do that pre-maps. What do you think are still the uses of variant attributes?
I think so.
It seems that for me, it replaces like 90% of the times I use variant attributes, but I'm just trying to see what. Obviously, the only thing I can think of is that you can kind of add metadata to a data type, with the variant attributes. But I don't really know what the purposes that they serve. But
for me, that if you're passing sort of flexible data, if you have some system that passes flexible data, so you need to be a variant, and then you want to add sort of attributes to that, then that's when I'd use a variant attribute still. But if you had the use case where you've got created variant purely for the use of variant attributes, so you can have a table of data, then I'd say maps pretty much replace that.
Is Actor Framework going to adopt sets maps instead of variant attributes? Comes from Guillaume Correa.
Brilliant.
Sorry.
To be honest, I don't know. I've not spoken to Stephen. Stephen Mercer would probably be the person who would know that better than me. As far as I know, there's no plans to do any major rewrites of the Actor framework, so unless it's broken, I don't think they'll go and fix that, but I could be wrong. Any other questions at all? In which case, thank you very much, and we'll move on to the next session, shall we?